Hello, everyone, and welcome back to the cycle of seminars of the Astronomy Department of IAG. The speaker of this week is Dr. Marina Trevisan. Thank you, Marina, for accepting this invitation. And Marina got her PhD here at IAG. And since 2018, she is a professor at Universidade Federal do Rio Grande do Sul. Today, Marina is going to present the seminar, What is Triggering Star Formation in Very Young Galaxies in the Local Universe. Questions will be asked after the presentation, and if you are following the seminar from our YouTube channel, you can write down your questions in the chat, and they will be redirected to Marina by the end of the talk. And before the seminar begins, I would like to ask everyone at Google Meet to please turn off your microphones and cameras throughout the talk. And Marina, you can start whenever you're ready.
Okay, thank you very much, Guilherme, for the introduction, and thank you for the invitation. It's always a pleasure to be back, even virtually, to IAG. So today, as Guilherme said, I'm going to talk about very young galaxies in the local universe. So I'll start presenting. Can you see the slide?
We can, it's perfect.
Okay. So I'm going to talk about what is triggering the star formation in very young galaxies in the local universe. So before talking about very young galaxies, I'm going just to say that a big problem today in cosmology is to understand how galaxies were formed and how they evolve. So it seems to be a very simple question, but it's basically 14 billion years of history. Basically, we try to understand how the first galaxies was formed and how they evolved until what we observe today. Different types, different properties. And one way to tackle this question, to address this question, is to trace the star formation history of the galaxies, to trace how they formed their stars along their history. So many observations indicate that, on average, the galaxies, the star formation rate of the galaxies, I mean the history of the star formation, it started increasing at high redshift, and it reached the peak at around redshift 2. It means 10 billion years ago, and then we see a decline in the star formation rate of galaxies. So it means that it seems that the galaxies were very efficient in forming stars around 10 billion years ago, and today they don't form many stars as they did in the past. But this is an average behavior. It's not the star formation history of galaxies can differ from one galaxy to other galaxies. So this is an average. If all galaxies if it was the case, all galaxies follow this star formation history, so less than 5% of the stars in a galaxy would be formed recently in the past 1 billion years. But it's not the case because it's not the star formation history of galaxies is not always the same. So this is what Dressler and collaborators found, for example, at a redshift below 1. It means below that peak that was in redshift 2. So more recently, Dressler, they found galaxies that were massive and formed a huge amount of stars in the past 1 billion years from the 2 billion years from the observation. They called these galaxies late bloomers. So it means that the universe was very efficient in forming stars around redshift 2, but these galaxies, they were forming a lot of stars at later times. So they traced here, as a result, they show in their paper, a result of the fraction of late bloomers. It means the fraction they observed a sample of galaxies and the fraction of those galaxies that are late bloomers from redshift around 0.7 until redshift 0.3. And what they see is that around for galaxies with masses around 10 to the 10 solar masses, almost 40% of them are late bloomers at redshift 0.7. And it decreases with stellar mass. So more massive galaxies, they tend to be older. They tend to have more a large amount of old stars than less massive galaxies. And this fraction decreases as the time passes. So at redshift 3.3, So the fraction of these late bloomers, these very young galaxies in redshift below 1, it decreases to less than 10%. But even at redshift 0, we observe galaxies that are very young, and these galaxies usually they are dwarf galaxies, very low mass galaxies, for example, as Zwicky 18. These galaxies, there are many studies that show that they claim that almost all the stars in these galaxies, in this galaxy Zwicky 18 in particular, were formed in the past 1 gigayear. So it means it was born very, very recently, below redshift 0.1. Other studies show that no, it's maybe there are old stars in these galaxies, of course, old population, but even with this old population of stars, the fraction of young stars in these galaxies is much, much higher than the normal, in normal galaxies. So, and this is very weird because this is a completely different behavior if we take into account the average behavior of all galaxies that I showed in two slides before. Since the peak of the star formation in the universe was at redshift 2, so how we can see these galaxies being formed now? So it's puzzling to understand what's going on, why these galaxies are forming a large amount of stars just now. So when we look at Zwicky 18, so we start asking some questions. So for example, is Zwicky 18 a special galaxies, or there are more like Zwicky 18? Are they frequent in the local universe? So it's common to find galaxies that are forming a large fraction of stars just recently. And if we find these galaxies, what does make VYGs, very young galaxies, different from other galaxies? Why they are young? And what is triggering the star formation in these galaxies? So we try to answer these questions to understand these very young systems. We are conducting a series of studies. From the frequency of these very young galaxies in the local universe, from the modeling from the theoretical point of view and from observations. And in a third study, we are looking at the properties and environment, trying to understand what they are and why they are young. So just to be clear, from now on, VYG, very young galaxy, I'm talking about galaxies that form at least 50% of their stellar mass in the last 1 gigayear. So that's what we defined as a VYG. So just to summarize our results on the frequency of VYGs in the local universe, we analyzed a sample of galaxies from the Sloan Digital Sky Survey. And we inferred their star formation history from the spectra, their spectra. So we used the stellar population synthesis to derive the star formation history. And here I show an example of a star formation history. Here is the look back time. It means that it's going back to the past here, 10 gigayears ago, and to the present here. Here is redshift 0. And here is the fraction of mass that was assembled in the galaxy. So it means, of course, the mass of the galaxy increases and reaches 100%. That is the mass of the galaxy that as it has today. So we interpolated this star formation history, and we computed the age 50. It means the age when the galaxy formed 50% of its stellar mass. And a VYG is a galaxy that has age 50 less than 1 gigayear. It means formed 50% of the stars in the past 1 gigayear, at least. So just to mention, one problem that we have with the Sloan Digital Sky Survey is that since we are inferring the star formation history from the spectra, and the spectra is observed through a fiber that has a size, an aperture of 3 arc seconds, it means that we are not seeing the whole galaxy. We're not seeing we are just seeing the center and only the inner parts. So this is a problem with this SDSS that we try to go around it by selecting only galaxies that are bluer at the outer parts than in the part that is observed by the fiber. So it means that if it's young within the fiber, it will be young outside the fiber as well, because we require that the galaxy must be bluer outside. So it's not a good thing. It can introduce some bias in the sample, but that's what we can do just to be sure that we are looking at the VYGs, the very young galaxies. Okay, I'm just going to summarize the two first studies on the frequencies of VYGs in the local universe with this figure. So I'm not going into many details, but what we see in on the fraction of very young galaxies is that the fraction is higher for low mass galaxies, as expected. Low mass systems, they tend to be younger and have a larger fraction of young stellar populations, and it decreases with the stellar mass. So this is the fraction, this is the stellar mass. And here, what I show here as the shaded areas are the results from observations. Here is the fraction inferred from the observations using SDSS, using different codes and models for the stellar population synthesis. And here is Starlight, here is Vespa with two different stellar population models. And as the symbols, they indicate different analytical and semi-analytical models of galaxy formation. And what you see is that in the observations, there are discrepancies among the theoretical models. There are discrepancies, and it's difficult to tell, to really be sure about the fraction of very young galaxies in the local universe, because different models and different approaches for the analysis of the data leads to different results. But this is interesting because it seems that we can use the fraction of very young galaxies to put constraints on models of galaxy formation, the theoretical models of galaxy formation, and also on the modeling of stellar population synthesis. So we can use this as to put constraints. But now to look in more detail what these systems are, because we found them regardless what we use to analyze the SDSS data. We see that we do find galaxies that are young. So here we are going to look at them in more detail and try to understand what's going on. So since there is disagreement between different approaches to analyze the data and extract the star formation history, what we did to select a clean sample of VYGs is to select only those galaxies that are young, according to the three different models that we used. So this to make sure, there is an agreement among all the three models. And besides, we selected only galaxies that have a spectra with good signal to noise. And again, we select only those galaxies that are bluer in the outer parts, bluer than the part that is observed with the SDSS fiber. So, of course, we reduce the sample a lot because depending on the model, we find thousands of VYGs, but since we put this extra criteria to select the sample, we end up with a sample of 207 VYGs. And to understand how they differ from normal galaxies, we selected a control sample of galaxies that are at similar redshifts. They have similar stellar masses. They also have the same color gradient, because we don't know the kind of biases that we can introduce by selecting only galaxies that are bluer in the outskirts, in the outer parts. And to To control a little bit the aperture effect of the fiber, we also selected the control sample. They have the same similar apparent sizes. So to be sure that we are observing a similar fraction of the galaxy within the SDSS fiber. So we selected a sample with more than 1,200 galaxies. And here I show the distribution of redshift, the stellar mass, the gradient, the difference of the G minus I color, and the apparent size are 50 of the VYGs, which are indicated in blue, and the control sample galaxies, which are indicated as or in orange. So they have, as I said, they were selected to have similar distribution in all these quantities, all these properties. So when we compare the properties of the VYGs with this control sample, we are sure that they are very similar in these properties. So I'll try to be to talk fast here, because there is a lot of results, but I don't want you to get bored with all the results that I'm going to present. So I'll try to be to don't talk much, but just as just to summarize, we investigated the VYG properties. We investigated the colors and the star formation rates of VYGs and compared with the control sample. We analyzed their morphology and structural parameters. We analyzed the T-types, the concentration, asymmetry, and smoothness, which are morphometrical parameters. We also analyzed the gas and the dust content of VYGs. We computed the oxygen abundance of the gas. We also analyzed the fraction of neutral gas in VYGs, and also the internal extinction and dust content of VYGs. So I'll try to summarize here the main results. So what we did is the following. We compared the properties of the VYGs, which are indicated in blue here, with the control sample, which is in orange. Here I show the color, here I show the star formation rate, and as a function of the stellar mass. And since the control sample, it's difficult to define a control sample with exactly the same distribution of stellar mass, because we have a lot of VYGs that are very low mass galaxies, and SDSS is not very good to observe very low mass galaxies. So there is a small difference. So just to be sure that this won't introduce any bias in our comparison, what we did, we fitted the relation between the property and as a function of the stellar mass, and we analyzed the residuals from this relation. And here what we see in summary that the VYGs, they are bluer, they tend to be bluer than the control sample as expected, and they have higher star formation rates as also expected. This is expected, but other properties, the results is not so obvious. For example, here we analyze the T-types. High values of T-types related to irregular galaxies, and low values, negative values, are elliptical galaxies. So what we see is that the VYGs, the morphology is not very different from the control sample galaxies, but we find an excess of elliptical systems. It means galaxy VYGs with T-types that are negative. And these are this kind of galaxy here. These are the blue compact dwarfs, like one Zwicky 18, for example. It's a compact galaxy that is very young. So we find an excess of this kind of system in the VYG sample that we don't see in the control sample. This is the difference in morphology. We also find here is the concentration and the surface brightness as a function of the stellar mass. And again, we fit the relation and analyze the residuals. And what we see is that the VYGs, they are more concentrated, they have higher concentration parameters, and they tend to have a higher surface brightness. We can see it very clearly here in the histograms of the residuals. They are also more asymmetric, and they are more clumpy than the control sample galaxies. And here we show the symmetry parameter and the smoothness parameter. And we also analyzed the VYG gas content, the oxygen abundances. And for this property, we don't see any significant difference from the control sample galaxy. But they have a higher fraction of neutral gas. We used the alpha-alpha survey to compute the fraction of neutral gas of VYGs. And what we see here in the blue points here, they tend to be higher than the control sample, which are indicated in orange. Don't worry if you miss something, because I'm going to summarize all the results in a moment. But before that, let's talk about the environment. So we see how the VYGs are. Now we want to understand, to look where they are. So we look at the local environment, the group environment, and the large-scale environment. It means voids and filaments. So first, we look at the nearest neighbor. Just look around the VYG and look what is around it. And we looked the VYG, the sample of the galaxy, and we looked at 200 kiloparsecs around it, and to see if there are neighbors and or higher concentration of neighbors. So we see that almost half of the VYGs in the control sample galaxies, they are very isolated. There is nothing within 200 kiloparsecs around them. But for those that they have a companion, the VYGs, they tend to be closer to their nearest neighbor than the control sample galaxy. Here I show the distance to the closest neighbor as a function of the stellar mass. And what I see is that the VYGs that are indicated in blue, they tend to be closer to the nearest neighbor than the control sample galaxy. And not only that, but when we analyze the fraction of mergers within the control sample and the VYG sample, what we see is that the fraction of merging systems is twice among VYGs compared to the control sample galaxies. And this doesn't matter what we use to define a merger, because it's very difficult to define it, to identify a merger. To have, for example, we have catalogs of galaxy morphology, which provide us with the probability of being a merger. For example, Galaxy Zoo, and the catalog by Diaz Dominguez Sanchez. They provide us with the probability of the galaxy being a merging system. And to define if the galaxy is a merger or not, we can select a threshold in this probability, right? We can select, okay, the galaxy is a merger if the probability is greater than 80%, for example. But we did more than that, because it's kind of arbitrary to select a threshold for this probability. So we just investigated what would be the fraction if for different values, thresholds of this probability of being a merger. And the answer is that doesn't matter. Doesn't matter because of here in orange is the control sample, and here in blue is the VYG sample. And regardless of the probability threshold that we adopt, the fraction of mergers among VYGs is always two times higher than the fraction in the control sample galaxy. And doesn't matter if we use Galaxy Zoo or we use the catalog by Dominguez Sanchez. It's always twice. So it's much more likely to find a merger in the VYG sample. Looking at the images, it's very clear that it's not only the VYG that show the galaxy that shows signs of interaction, but also the neighbor. The neighbor also shows signs of interaction. So it's even more, it gives us a higher certainty that the system is really interacting with the neighbor. So to analyze this and quantify this, the number of VYGs that have signs of interaction with the neighbor, not only the VYG, but also the neighbor, we performed our own classification of merger, and we analyzed if there is a neighbor closer to the VYG, and if the neighbor also shows signs of interaction. And here, the results, just to summarize, what we see is that galaxies that show signs of interaction, both the galaxy and the neighbor, is 12% among the VYGs and half among the control sample galaxies. So it's another way, it's always twice as more likely to find interacting systems in the VYG sample. And finally, looking at where the galaxy are more global environment, we investigated if these VYGs, they are in groups or clusters. And what we found is that the VYGs, they tend to be, here is the fraction of galaxies as a function of distance to the center of groups or clusters here. And what we see is that the VYGs indicated in blue here, the fraction of central galaxies and galaxies, VYGs that are in the inner parts of low mass groups is higher when we compare to the fraction among the control sample galaxies. So it means that they tend to live in groups, low mass groups, and in the inner parts of low mass groups. So just to summarize, because I showed a lot of things, but those who I'm going to summarize what all the results I presented. So compared to the control sample galaxies, what the VYGs are bluer and have higher star formation rates, as expected, as I said. They contain a higher fraction of spheroidal systems like these blue compact galaxies here. But the T-types, it means the overall morphology, is not that different from the control sample galaxies. They have higher concentration and higher surface brightness. They are more asymmetric and clumpy, like this one. I show example of galaxies that are very asymmetric and clumpy. They have higher fractions of atomic gas, and they have higher values of internal extinction, indicating the presence of dust, but they have the same gas metallicity. And regarding the environment, they are at smaller distance from the closest neighbor. They are more likely to be interacting and merging with a neighbor, with a close neighbor. And they are more likely to be found in the inner parts of low mass groups. But I didn't show it, but the results on the large scale environment, they have the same distribution relative to the cosmic filaments and to the voids. So all these properties, they are different from a normal galaxy, like the control sample galaxies. So just to have in mind what I'm talking about here, and so there are some examples of VYGs. Here is the less massive galaxies in our galaxy in our sample, and here is the most massive in our sample. The stellar mass is almost 10 to the 10.6, and we see that a lot of them are interacting. They are very clumpy, asymmetric, as I showed in the results in the summary in the previous slide. So what is the relation? For example, I was talking about Zwicky 18 in the beginning of the talk, and what is the relation of these VYGs in this sample that we analyzed here and the Zwicky 18? They very likely they are not the same type of galaxy because, for example, Zwicky 18, one of the main properties is that it's a very low metallicity galaxy, and our VYGs, they are not. And Zwicky 18 appear to be very isolated, so it's unclear what is triggering the star formation in this galaxy, in this dwarf galaxy. And our VYGs is exactly the opposite. We see that they tend to have companions, and they tend to live and to be found in the inner parts of groups. So they are not isolated. They tend to have companion. In any case, it's very difficult to compare our sample with galaxies like Zwicky 18, because the mass regime is different. Because our galaxies, they are more massive than galaxies like Zwicky 18, because these systems, they are very low mass galaxies, and we don't have this kind of galaxies in our sample, because SDSS, it's very difficult to observe these very low mass galaxies. And Zwicky 18, of course, it's a very nearby object, and galaxies like Zwicky 18 is very nearby object, so it's very difficult to define the environment because of the peculiar velocities at low distance. So, but in any case, it's the VYGs that we analyzed and other young systems like Zwicky 18 is that they are very likely to be different. They are not the same kind of object. And the relation of these VYGs at redshift 0 and the late bloomers at higher redshift. What we see is that we compare the fraction of VYGs in the local universe at redshift 0, and we can see that here is the fraction of late bloomers from the Dressler study. And what we see is that the fraction of VYGs in the local universe can be seen as extrapolation of their results at higher redshift, because here's the fraction of very young galaxies and here is the redshift. It can be seen as extrapolation. Of course, there's a large scatter here, but maybe it's a similar type of object, but at lower redshifts. But in any case, it's difficult to compare because, it's difficult to compare because these galaxies studied by Dressler and collaborators, they are more massive than our galaxies. So it's difficult to compare the results, but they may be the same kind of object. And okay. And maybe the main result that we can conclude from all this study is that VYGs are very likely to be products of interaction and mergers. So we know that mergers and interaction can disturb, can cause disturbance in the gas in the galaxy and trigger star formation. And it seems that that's what's going on. That's what's happening in these very young galaxies. And this is many results many of our results point to this direction. For example, VYGs, they are more likely to have a companion. They are closer to their companion. They show sign of interactions. The fraction of galaxies that are merging in the VYG sample is twice the fraction of of galaxies in the control sample that are merging. They are more likely to be found in the inner parts of low mass groups where mergers are more likely to occur. They are more clumpy and asymmetric, which can be a sign of interaction because that's the result of interaction can make the galaxy clumpy and asymmetric. They have higher concentration, which also can be a consequence of mergers because mergers can make the gas lose angular momentum and go to the center of the galaxy and cause a central burst. So this could also be a consequence of the merger and interactions. And they have more internal extinction, which we may think that can be associated with a merger like the U-lyrics. And besides, on top of all these results, in the paper by Tweed, where we analyzed the analytical semi-analytical models of galaxy formation to predict the fraction of VYGs, we see that VYGs are usually associated with a recent major merger of halos. So it means that even in the theoretical point of view, it seems that mergers are making galaxies young. So, but we cannot say that all the VYGs that we analyzed are a consequence of mergers, because many of our VYGs, they are isolated, they don't show any sign of interaction or mergers, so maybe there are other mechanisms that may be triggering the star formation and formation of a huge amount of stars in a galaxy in the local universe. So just to summarize all the results we investigated. So we investigated here in this, what I presented, present the properties and the environment of very young galaxies in the local universe. Those galaxies that form at least 50% of their stellar mass in the past 1 billion years. And what we see is that these VYGs that we studied and the ones weak 18-like galaxies, they are probably different in nature, because our VYGs, they are not low metallicity galaxies, and ones weak 18, it's a very low metallicity galaxy. And the main conclusion that we can, the take-home message here is that probably gas-rich and merger and interaction is what is it's a very important mechanism in triggering star formation, and with very high star formation rates in the local universe. So this might be what explain a lot of VYGs in the local universe, but maybe not all the VYGs. So maybe other mechanisms are also playing a role in this scenario, and also triggering the star formation. So we are going further, trying to understand these other mechanisms that may be acting here to produce these VYGs. And we are, for example, conducting a study with radio observations to look the distribution of the H1 gas around the galaxies. And also we are looking at the hydrodynamical simulations to see the properties of the VYGs in simulations, and also the progenitors, try to understand what the history of these objects are. So this is, so I leave you here with the summary of this talk, and I'm open to questions now.
Thank you so much, Marina, for your nice talk. It was all quite clear, and in particular, the figures were quite helpful. And we have a lot of people with their hands raised. First of all, Eduardo Teles has a question. Go ahead, Eduardo.
Hi, Marina.
Hi.
Marisa. Very nice talk. I would have to have a whole session to discuss a whole lot of things with you. The first slide that you showed about environment, just to clarify, you mentioned that half of your sample, or almost half of your sample, are isolated. Right?
Yes. Yes.
So your
within 200,
analysis,
but within 200 kiloparsecs.
Right. Okay. Very well. You didn't show any spectrum of these galaxies. Do they have H delta absorptions or
absorptions? Yeah, most of them. Yeah, we have a lot of starburst galaxies that are emission everywhere, and we have few galaxies which H delta it's already in absorption. Yes, but
because if they have this intermediate age population, or less than 1 gig a year, you would expect that to show some of these spectral features in the spectrum, maybe, no?
No, they show the young population. No, it's very clear. No, it's very the young population is very clear. They have because I don't know the fraction, but a lot of them, they have H delta in emission. So, but so it's already forming. It's still forming stars, but we have we have
that shows the population is ionizing.
Yeah.
So that means that it's very, very young. Well, your definition of young galaxies are ones that have most of the mass in intermediate age, right?
No, yeah, it
Not
must
giga
have
year.
at least 50% of the stellar mass was formed in the last 1 billion year. It doesn't mean that it doesn't have an old population. It can have
Right.
an old population, but at least 50% was formed in the last 1 billion year.
That goes my last question. I'll leave to the others, but my last question is exactly that. Can you distinguish the 1 giga year population from a 10 giga year population in your analysis?
So, yeah, I did some simulation just to see if we are really seeing what we think that we are seeing. And what I simulated a spectra with a young population, different fractions of a young population, and old population with different fractions and different ages. I try to vary. And what I can say, I just use the starlight. So here, just remember that here, the VYGs that I presented in the talk, they are VYG according to 3 different stellar population synthesis analysis. But I just analyzed with a starlight, and what I can tell you is that if the starlight finds that a galaxy is young, at least 40% of the stellar mass, it can be wrong, maybe it's not 50, but it's at least 40% of the stellar mass is young. Only starlight. So if it's less than that, it's very unlikely that a starlight is going to classify the galaxy as a VYG. And yes, we worried about that because we know that it's a can of worms. Stellar population synthesis is just, yes, we cannot trust that much. But yeah, we performed this analysis and with simulations.
Oh, yeah, thank you. We can discuss more about that in some time in the future. Thank you very much for now.
Okay.
Thank you, Eduardo. Now, Marcelo has his hand raised. Go ahead, Marcelo.
Okay, can you hear me?
Yes.
Hi, Marina. Thank you for your presentation. Very nice work. I would like to thank that you answering many emails some months ago about the conditional luminosity functions.
Oh, it was you. Nice to meet you.
Very nice to meet you.
Okay.
Okay, so my first question was already answered. And my second one is kind of a curiosity. If one intends to search for interacting galaxies, do you think looking for these VYGs is a good way to start the investigation? Or
yeah, if you want to gas-rich interacting galaxies, yes.
Yeah.
Yes, it's a good way to start.
Okay.
Yeah, but if if there is no gas in the interaction or 2 elliptical galaxies, they are not being young because you need gas to form stars. But if it's a gas-rich interaction or merger, so probably we'll see a burst and a huge amount of young stars.
Okay. Yeah. Okay, nice. Thank you.
Thank you, Marcelo. And Professor Laerte has his hand raised. Go ahead, Laerte.
Hi, Marina. Very nice talk. As
Thank
Edu
you.
said, there are many things to discuss. But first, curiosity. You adopt a criterion that the galaxy should be bluer in the outside than the inside. Well, so you are assuming a priori inside-out scenario for galaxy formation. I wonder what if you have examples of galaxies otherwise. I don't know. Just a curiosity.
That are redder outside?
Yes.
Yes, so because when we apply this selection, this criterion, basically we eliminate half of the sample because it's a lot of galaxies. They are blue. Sometimes they are not that red outside, but they are redder outside. So we cannot be sure what's going on outside because if we try to infer if the galaxy is young or not, just based on the fiber on the spectrum, so we need to apply some criterion because we don't know what's going on outside. But you are right. We are aware of that because everything that I presented, that's a good point, because everything that I presented here applies to this sample that have a color gradient that they are bluer outside. So Yeah, but that's what we can do with SDSS. But
Yeah,
you were right. You were right.
No, this criterion raised me the possibility of investigate if you have a very young population outside. Even this might be an interesting object because
Yes.
you know. Because maybe it's better I enter in my other question because it's somewhat related to this one. My impression is that these your galaxies are essentially, say, a gas-rich dwarf that suffered a recent merger, and this recent merger increased its mass by, say, 50% or a large fraction anyway. This is more or less a good definition of what's going on.
Yes. It seems that in our sample, the merger is an important mechanism. So these VYGs, they are the merger is exactly what's causing the burst of star formation. So yeah, that's a good.
The point is
conclusion.
because the metallicity, because since the metallicity is high for your objects,
yes.
I suspected that and they are small galaxies. Previously to this star formation episode, probably they were already dwarfs, formed dwarfs. I don't know. Well, just a speculation. Huh? That,
yes, but they are dwarfs and also intermediate mass galaxies. They are not all dwarfs because a lot of them, they have more than 10 to the 10 solar masses. So yes, again, we have a low metallicity galaxies in our sample, but it's a very, very low fraction, and they are in the low mass end in the distribution of mass. But it seems to me that low metallicity galaxies, they are low mass galaxies. They cannot be. So here we are looking at young galaxies, but they are higher mass galaxies. So they are not the same thing. They are not the same thing. So probably that's it. They were galaxies that merged and with a lot of gas and triggered the star formation.
Okay, Marina, thank you, and congratulations for the talk again.
Thank you.
Thank you, Laerte. Now, Reinaldo has his hand raised, but Reinaldo, can I ask a question before you? Because I have a question that is very similar to the one from Laerte. Okay, so following the question from Professor Laerte, I actually imagined something different. I imagined that these galaxies, since they are in the cores of low mass groups, they were like interacting with the most massive galaxy in the group. For instance, they are falling into the halo of a massive galaxy, and then this info of this galaxy and the interaction with the mass or the gravitational potential of the massive host is triggering star formation. And in this scenario, like they would be like something like extreme examples of the Large Magellanic Cloud, for instance. That's what I imagine. But do they have to like crash into another galaxy to
No, exactly. That's what, because yes, that's exactly what I said in the end of the talk, because merger and interaction, it seems to be a very important mechanism, but maybe it's not the only mechanism, because a lot of our galaxies, they are isolated. They don't seem to be interacting with anything. So some other mechanism, but to be it can be another mechanism. So not necessarily a merger. Even because we see VYGs in clusters as well, so this can be the case in clusters, which the potential is higher, and the interaction, the potential of the cluster itself can cause something. So yeah, it can be other mechanisms, but
since there are some of these,
we need to investigate because
Now that you said that some of these galaxies are isolated, maybe this is the case where when they are isolated, at least I imagine that when they are isolated, like they effectively crashed into another galaxy of similar mass, and they suffer like a major merger, and from time to time, maybe they are like they are experiencing this kind of falling into a more massive halo. I don't know.
Yeah, but if they are isolated, they're very unlikely to find another galaxy to merge with. But that's why I said merger interaction. It seems to be an important mechanism, but not the only one. not the only one. Yeah.
Okay,
For
thank you.
example, the sample that we are analyzing now, because we are still analyzing the data, but the sample that we observed with we have a radio observations, we see that there is a lot of gas, sometimes off-centered. So it seems that it's some other object system that is gas rich, but we don't see the stars because in the optical it doesn't appear. So something is going on there, that there's some gas rich system that is merging, but we don't see in the optical images. So we are still investigating that and try to understand what is going on, but it would be a different thing than merging between two galaxies. So
Yeah, I see. Okay, thank you. I will have another question, but I will let Reinaldo go.
okay.
Mine is very simple. First, congratulations, Marina. I think my impression is that this study is a very careful one, and congratulations for you and your collaborations, and thanks for the talk. Very interesting. Maybe it's something that I did not understand very well. You called attention that these VYGs, they have a higher fractions of atomic gas. You mean atomic neutral gas or
neutral? Yeah, H1. Yeah.
Oh, okay.
Yeah.
Is it expected in some galaxy that is actively forming stars, or for me it's counterintuitive? This.
No, yeah, because they have a large fraction is ionized, but to be ionized, you have to have gas as well. So, and probably is because you have regions where the gas is ionized, but in the other parts it's neutral. So yeah, it has a large fraction of neutral gas.
Okay, and not compared to ionized, but in general, a lot of gas. Is it?
So if you look, because this is it is a public survey, it's alpha. It's very easy. If you have a look in the alpha survey, you see and combine the data with Sloan, and you see that low mass galaxies, they have a very high the fraction of gas is very high. So there is a trend as the mass increases, the fraction of gas decreases. This is a trend, but these galaxies, they are low mass, but even for the fixed stellar mass, they have a higher fraction of gas than a normal galaxy. That's what I meant. Because low mass galaxies, they have high, the fraction of gas is high, but the VYGs, it's even higher.
Oh, okay. Now I understand. I thought for a moment that it was compared to ionized gas, or
no.
Okay.
It's just compared with the control sample. I just computed the fraction of neutral gas in the control sample and the VYGs, and the control sample. The fraction is also high. It's almost it's 95% of the galaxy. The mass is gas, but the fraction among the VYGs is even higher. It's almost 100%.
Perfect. Thank you.
Thank you, Professor Reinaldo. And now we don't have anyone else with the hands raised. So maybe we can use this opportunity to end the seminar in time for once. Okay. And then we can continue here in Google Meet, just chatting about other more specific doubts that someone might have.
Okay.
I would like to thank you again, Marina, on behalf of the department and the organizing committee of the seminars. Thank you so much. The presentation was quite clear. And Kishan, I think you can end the transmission now.